Okay, good morning. Let's dive straight away into our example 1 for AC power. And I'll pick up where we stopped yesterday. Any questions before I begin? Did anyone review the solutions? I keep asking in the hope that students actually did something. Okay, all right. So we stopped at this step yesterday where we found the total current I by applying Ohm's law, right? So any questions thus far? Just a recap. We have a RLC circuit. We are asked to find the total power for all components, meaning in this case, we'll include the source also as a component. So find power for RLC as well as the source. So we can take two approaches. If you wish to find the total power for the source, we can find the power for the individual components. All of the energy that is absorbed by all the components has to come from all the sources. In this case, there's only one source, meaning if we add up all of the power for the components, it should equal the total energy supplied by the source. So you can find the individual RLC powers, add it up, and you get the source power. Or you find the source power, and then you separate out the individual components. That would give you the individual P and Q. Make sense? Right? So again, there are a certain number of equations, right? There are not just two primary sets of equations. One is here. Right? You have, in all cases, you need either the voltage or the current, right? If it's a source, it doesn't have resistance or reactance, so you need both voltage and current. If it's a component like a resistor, inductor, or capacitor, you need at least the resistance or the reactance, and then either the voltage or the current. So depending on which equation you like to use, you need to determine those quantities. And then, of course, we also have these equations where you will need the voltage and the current. And then the phase difference between the voltage and the current would give you the power angle theta. And so you'd be able to determine the power in multiple different ways or multiple different pathways. Which approach you like to take is up to you as an engineer. Okay. And that is a choice you'd have to make every day as a working engineer, whether you have your own business, own startup, whether you go work for a corporation, small or big. They always want you to find the most efficient approach, most efficient solution. And most efficient usually means the best solution at the lowest cost with the quickest turnaround time. Okay, so let's see. We have I. I is the total current that is flowing through the source, the inductor ZL, and ZRC, the parallel combination of the resistor and the capacitor, right? So we can find the voltage across the inductor, and we can find the voltage across the resistor capacitor combination by applying Ohm's law. Make sense? That is one approach. Then, if you take a look at the circuit diagram, what do we see? ZL and ZRC are in series. Voltage divided across a series combination of impedances or series combination of resistances. Voltage division. You can apply voltage division directly and find the voltages that way. So whether you have current or whether you have voltage, you can find power by applying both equations. So we have total current I, and from total current I, we can find the voltage across that resistor capacitor combination by applying Ohm's law, I times ZRC, or you can apply voltage division and find it that way, which is what I've done here. Apply voltage division and find it that way. Yes. Yes. So it doesn't really matter what component it is. In the end, we treat it like all resistors, whether in series or whether in parallel. The only difference is instead of like instead of simple numbers, we now have complex numbers. Yes. Yeah. So the question being asked is about the reduction of the circuit. And so the reduction of the circuit would take the same approach that we took in chapters 1 and 2. Meaning once we have the equivalent impedance diagram, we proceed as if they were all resistors. And that's why I always suggest to students, draw the diagram first and then write out the equations, and then you plug in the numbers. Once you have your approach outlined, if you start mixing up both at the same time, then it gets a little confusing. So when you're first starting out, I would always suggest derive your equations first and then plug in the numbers. Okay, so I would say take your VRC and VL and practice and see if you can obtain the same answers that I have. Okay, I obtained it using voltage division. You can try obtaining it using Ohm's law, I times ZRC. It's a simple calculation. You should be able to do it at this point. 10 with an angle of minus 180, that is the voltage across the resistor and the capacitor. And then I can find the individual currents, IR and IC. Okay, IR and IC. Now, note, I don't need to find the resistor current or the capacitor current. I can simply do V square over R or V square over X. I have the voltage, right? We have the voltage across the resistor and the capacitor. I can use these equations. This one, right here. If you have the voltage, you can use the bottom equations. If you have the current, you can use the middle equations. But I'm just showing the approach where you can find all quantities. Okay. As I said, it's not required, but because this is the teaching moment, well, I'm going over the procedure and steps, I'm showing you. So IR is 0.1, IC is also 0.1. Phase angles are different. Okay, phase angles are different. And obviously these values depend on the values of the components themselves. The resistor is also 100 ohms, and the impedance for the capacitor is also 100 ohms. Obviously, the resistor does not have any angle. Okay. So now you have voltage and you have current for both the resistor and the capacitor. You also have the current for the inductor. We never found the voltage for the inductor, but I will assign that as practice for students to do. Again, keep in mind, there's a big quiz on Monday, about 35, 40 minutes long. Yeah, based on AC analysis and AC power. And as I stated earlier, I'm repeating now, I will not assess AC power and AC analysis separately on the final exam. So show me your best work on Monday. Okay. All right, so we have the resistor current, capacitor current. Yeah, the resistor voltage, capacitor voltage. We can use two sets of equations to determine the power for resistor and capacitor. We can do the same for the inductor also. The inductor current is the same as the source current, I. We did not find, again, repeating that same point, we did not find the voltage across the inductor, but I will assign it as practice. You can find it directly. So on the left here are the set of equations where we use voltages to determine our power. And on the right, we have the currents that we use to determine the power. Same standard form. If you have voltage, it's V square over R or V square over X. If you have current, is I square times R, I square times X. X is, of course, the reactance. You can see left and right, doesn't matter which equation you choose, Your answers are exactly the same or should be the same. When you're a student and you're giving an exam, you might not have time to verify your answers. But when you are a working or practicing engineer, it would be expected of you to verify your answers or your solutions in multiple ways. Okay. And this is the purpose of showing you why. Because if your answers don't match up using multiple pathways, then, well, one of them should be incorrect or would be incorrect. So let's take a pause while you think over all of that. Let me know if you have any questions. Yes. Yeah. So the technique or the equation, basically, the technique is basically the same for both, but on the left, all I'm doing is I'm using voltages, and on the right, I'm using the currents for each quantity. So these are just the inductor, the resistor, and the capacitor, noted by the subscripts, R, L, and C. Resistor, of course, only has average power or real power, which is P, and inductors and capacitors have only Q. So it's only PR and not QR, because resistors don't have reactance, they don't have reactive power. Inductors and capacitors don't have resistance, so they don't have any real or average power. So on the left is basically the voltages for the components. On the right is the currents for those components. Yes. Everything. Holistic. And I will post, on Friday, and again I will post the announcement, and then I'll ensure that students know what to do. That is one of the purposes of this problem. This problem, as I stated, is a 2-in-1 problem. It's also AC analysis, and then after that we do AC power, meaning first we determine the voltages and currents, and then we use those to determine the power. Okay, so once you have the individual powers for the individual components, you can simply add it up, and you can obtain the total power being supplied by the source. And I should actually let's put a small subscript here, make it SS. S stands for the total complex power. And total complex power can belong to a source, or it could be a system, it could be an entire circuit that has multiple sources. In this case, there's only one source, so we're talking about total complex power being supplied or associated with that source. This equation, the logic we are using is law of conservation of energy. All of the power received by the three components has to equal the power being delivered or supplied by the source, right? So whether it's a simple circuit or whether it's a complex circuit with multiple sources and multiple components, you add up all of the resistive power together and you add up all of the reactive power together, which is what we have done here. You have one resistor, so there's only one P in there, right? 0.5, but there are two reactive components, L and C. So we take QL plus QC. QC will always be minus Eli the Iceman. Voltage for an inductor is always ahead of the current. So inductor always is pointing up, plus 90 degrees. So the impedance angle and the power angle for an inductor is always plus 90. For a capacitor, voltage always lags the current, so it's minus 90. So the impedance angle and the power angle for a capacitor is always minus. Okay, so the reactive power QC is always minus. So when you do QL, when you sum up QL and QC, QC is actually subtracted, right? So it becomes 1 VAR minus 0.5 VAR. Total power associated with the source is 0.5 plus J 0.5. Units, volt ampere, VA. VA. Okay. That would be the end of the problem or the end of your solution. You found the power for all 4 components. Below that is 2 more approaches to finding the total power. Make sense? Any questions? Okay. So the first approach is you find individual powers, RLC, and then you add it all up. You find the total source power. Second approach, you find the total power directly. Subscript S notes that you're trying to find the total power supplied by the source. So SS can be referred to as PS plus JQS. Now we can use the other set of equations from here. If you use these set of equations you can apply to any component. You can apply to a resistor, you can apply to an inductor or capacitor, and you can apply to any source. If it's a resistor, it's only P. If you have the resistor voltage, you have the resistor current, and you can find P. Or if you have the inductor voltage and inductor current, you can find Q. So again, either set of equations, it's fine. You decide which one you want to use. So in this case, if you wish to use this to determine source power, I can find by using the source voltage and the source current. And then theta is the difference between the voltage and current power angles. Don't need anything else. Theta V minus theta I. So P is VRMS, IRMS times cosine theta. I simply plug in the values and calculate both P as well as Q. So now, voltage, of course, is given to us. Current is something we determined, which is right here. All I need to do is plug it into the equation and find my answers. So voltage angle was minus 90. Current angle is minus 135, gives me a total power angle of plus 45 degrees. I have my voltage, I have my current. I find VRMS by dividing by √2, plug all the values in the equation, and I obtain the exact same answers. 0.5 watts and 0.5 VAR. Enter the values in the equation, and you get the same equation. Let's take a pause while you think on that. Let me know if you have any questions. Any questions? The steps make sense? This is kind of like a top-down approach. You found the total power being supplied by the source, but it does not give you the individual power for every single component. Okay. Total power being supplied by the source, you can equate it with P plus JQ. P is 0.5, Q, total Q in the system is 0.5. Since there's only one resistor, we can state resistor is 0.5 watts. But there are two reactive components. So this 0.5 is a combination of inductor and capacitor. And so we don't have individual powers for individual components. Okay, we still have to perform calculations to determine those. So this approach would work if you only need to find the total source power. Make sense? Right? Power triangles. If you take the total source power and you take those equations and you plot it on the real and imaginary axis, you get that power triangle. Real power P is on the real axis, 0.5 watts. Total Q is on the imaginary axis, y-axis. And in this case, it's 1 minus 0.5. So it's plus 0.5 pointing straight up. And so 0.5 VAR, you join those two together and you obtain the magnitude of S. Magnitude of S is also known as apparent power. Apparent power. Let me actually write it out here. I'll point it out here. Magnitude of S is also known as apparent power. The unit is still VA, right? The quantity is still S, and so the unit is also VA, volt ampere. Okay. So if you look at the power triangle, if you look at the power values, what do we see? The inductor requires 1 VAR, 1 volt ampere reactive, 1 VAR. And then the capacitor supplies half of that. Capacitor is 0.5 VAR. Remember, inductor points up, capacitor points down. So your inductor power required is 1. Capacitor brings it down by half. This would have been your total power required. This is the actual power required. This is without the capacitor. This is with the capacitor. Remember, when the switch is flipped, the source supplies all of that energy, 1 VAR. But after it reaches steady state, after the source supplies 1 VAR for the first cycle, the capacitor absorbs half of it and then supplies half of that power from that point on. So after it reaches steady state, the source only has to supply 0.5 and not the full 1 VAR. So the source requirements are now less. In this process, of designing and choosing, actually, capacitor reduces total Q required from the source. Because the required Q is now small, the power angle is small. So cosine of theta is high. Power factor is high, right? The smaller the angle, the higher the power factor. If it's all the way down to 0, cosine of 0 is 100%. For any other value, cosine is 1 or less. Highest possible is 1, which in real life is never possible or attainable. Okay, so power factor is basically how big or how small. Power factor of a system describes how small that power angle is. Okay, and designing a system and choosing the value of the capacitor to match up with your inductive loads is known as power factor correction, which for students who are taking the lab is lab 8. Okay, you have an inductive load, and then you design the system to determine the best value for capacitor to balance out that inductor. How many of you have finished a lab 8? Oh, last week? Yeah, it's just, yeah. It makes it worse because it's a Monday and a Tuesday. And so it's ahead in the week, and it's also like another week ahead. So yeah. But for everyone else who are not on those Monday, Tuesday schedule, like Wednesday, Thursday, Friday, they are all doing lab 8 like now this week. Yeah, the holidays, Monday holidays is, yeah. Okay. Power triangles, questions. Does it make more sense now? Lab 8. Unfortunately, it is what it is, you know. Any other questions? Yeah.
So the word is binary.
So there's, well, higher Q or higher P is, in all cases, you want your power requirements to be as low as possible. So let's say if it was, let's take a smartphone, right? Your mobile devices. You want your mobile devices to be as light as possible. So as light as possible, so you want the battery to be as small as possible. Batteries, by the way, are the biggest space occupiers in any mobile device. It occupies the most space. And so they always want, the reason they integrate the batteries is because they can remove the additional walls around a battery. So they can make it as thin as possible. Now, if your battery is smaller, you can make your device smaller, but then it doesn't last as long, right? So your power requirements are lower, but it doesn't last as long. So there's always system trade-offs. So the more bigger batteries you have, the longer it will take to charge, the more power it requires from your adapter. Okay. So initially, when smartphones or regular devices first came out, they were the standard spec. USB port for a computer is like 0.5 amps. Okay. All the chargers that came out would supply like 1 amp. So if you look at, like, you know, the first iPhone, the first Android phones, the smartphones that came out, HTC, HD2, and all of those, they would come with a 1 amp charger. So 1 amp times 5 volts gives you a 5-watt charger. Then came fast chargers, and they increased the 1 amp to like 1.5 and 2 amps. So now it's a 10-watt charger. So the more current, so the USB spec doesn't change. It still stays same at 5 volts. Okay, it still stays at 5 volts. They increased it a little bit. Tolerance is increased like 5.1, 5.2 volts. You can't increase much beyond that because that's the actual spec. That's what all ICs and chips, you know, handle. 5 volts. But you keep increasing the current requirement increases, the faster the current comes. I mean, the higher the value of the current, the faster it receives. I'm jumbling up my words. Step back. The faster, the higher the amount of current, the more power is delivered. The more power that you deliver, the faster it charges. So if you connect your smartphone to, like, let's say a computer, it charges slower. The reason is because the computer can only supply 0.5 amps. If it's 0.5 amps, the power is now reduced. The power being received by your smartphone is only 2.5 watts. If you connect a 1 amp charger, then it's only 5 watts. If you connect a 2 amp charger, it's 10 watts. If you connect a 10 amp charger, it's 50 watts, which would blow out your smartphone if it doesn't have protection. But smartphones, one of the smart capabilities for every device is that it will tell the charger, I cannot accept 10 amps of current. I only need 2. Right? That's why manufacturers always state you only use the chargers that we provide. Well, of course, there's a reason for that. It's basically, safety issues. Plus, they also want to sell, their more expensive chargers. So there are charging systems that are capable of very fast charging, but companies don't implement those because there are trade-offs. My phone can charge from like 0 to 100 in like 20 minutes, like 240-watt charger. And so it's capable of doing like super fast charging. So it's a system trade-off, as I said. You always want the power requirement to be low because the faster it charges, the more energy is transferred. The more energy is transferred, the more hotter things get. And the more hotter the things get, as temperature rises, system deteriorates that much faster. So again, it's always the question being asked, I think it was, what is the optimal value of power? Always as low as possible. If you look at your adapters, it'll always have a power spec rating. The newer USB spec, USB-C specs, you can use them for charging. You can use them to charge any device. So they can go up to like 20 volts, 30 volts, even 50 volts. So you can use those to charge your laptops. You can also use it to charge your smartphones. There, the USB spec voltage has increased and the current has also increased. So you increase both V and I. And so now you're transferring a whole lot more power all at once. Okay. Make sense? All right. One thing here, I like going on tangents, but then it takes up class time. Fortunately, we have time. One last approach is to use the equation half VI asterisk. Okay, that's the total power for the source. If you have the voltage, you have the current, you can apply this equation, half VI asterisk. And the asterisk notes that is the complex conjugate of that quantity, only of the current, not of the voltage. Okay. This is only of the current. So the asterisk or star, if you want to call it that, is the complex conjugate. It flips the value around the real axis. Plus becomes a minus, minus becomes plus. And you obtain the exact same answer, 0.5 plus J0.5. Okay. So a third approach. But again, it just gives you the total complex power by the source. It doesn't give you anything else. Okay, not individual quantities. So 3 different approaches to finding the total source power. Okay, let's look at example 2. This is very interesting. So you have a circuit. It's actually not a circuit diagram. It's just a system diagram. There is a source. There's a voltage source in there. Value is given. And then you are given loads A and B. You are not told whether it's a resistor or inductor or capacitor. It's simply a load A and B. Okay. And those loads A and B seem to be comprised of both resistors, capacitors, and inductors. Okay. But nothing is given to us. We are asked to find the total complex power for the source and draw power triangles for all 3, for the source and for A and B. Now, as engineers, you have to look at the entire system, look at the information that is provided to you. In this case, a ton of information is in the units. Okay. So when you look at a system, extract as much information as you can. In this case, we're going to look at A and B individually and then determine what kind of components they are and how we can use these values to draw the power triangles and then determine the individual values. Okay. So 1 voltage source, 2 loads, element A, element B. Element A has units of VA. Element B has units of watts, W. Going back to this slide where we introduced the individual units. VA, volt ampere, notes S, the complex power. W is for real power or average power, and VAR is for Q, reactive power. So if element A has 10,000 volt ampere, and we are talking about a power triangle. Power triangle has P, has Q, and has magnitude of S. Then the 10 kVA refers to the magnitude of S. Magnitude of S. Make sense? Similarly, you have 5,000 watts for element B. Watts, straight up, average power, P. Average power, P, 5 kilowatts. Okay, now the three subscripts I've used is S for the source and A and B for the two loads. Okay, so let's look at the first one. What do we have? This is 10 kVA. It refers to apparent power, SA, so 10 kVA. Then power factor is stated as 0.5 leading. 0.5 leading. The numbers and the words both have meaning. Okay. The numbers indicate that there is an angle. If it was 1, if the power factor is 1, that means that it's lying flat on the x-axis. It's lying flat on the x-axis, meaning everything is just real power. But if it states it's 0.5 leading, meaning it has an angle. If it has an angle, it means it has some real component and it has some reactive component. Again, if it was 1, if power factor was 1, meaning it would be cosine theta. Cosine of 0 would be 1. So theta would be 0, meaning it would be lying flat on the x-axis, meaning it would only be real power. It would not be any reactive power. But because it says 0.5, 0.5 means there is an angle present. If there is an angle, it means there is real power, there is reactive power, and then there is apparent power, magnitude of S. And that refers to element A. Again, as I said, I like this problem. It's interesting because all of the information is not given to you. We have to infer, we have to deduce, we have to conclude from the information that is presented to us. Same thing with element B. Element B is given as 0.7 lagging. 0.7 indicates, again, that there is an angle. Cosine of theta is 0.7, meaning theta has some value. If it was 1, it would be cosine of theta would be 1, meaning theta would be 0. But both cases, you have 0.5, you have 0.7. So you do cos inverse or arc cos of 0.5 and 0.7 to find that power angle. That's what that 0.5 and 0.7 indicate. The leading and lagging is straightforward. Eli the Iceman, voltage for an inductor always leads the current. The current is the reference for power factor. Remember, current is always voltage is the reference for power factor. The status of the current is the status of the power factor. If current lags, power factor is lagging. If current leads, power factor is leading. Current always lags the voltage in an inductor, and in a capacitor, current always leads. So if it says power factor lagging, it is always, always, always an inductor. If it says power factor is leading, it always, always, always means it's a capacitor. So this is a capacitor. This has an inductor. It also has a resistor in there because there is a power angle. Okay, there is some real power associated with both. So it is R plus C and R plus L. R plus C and R plus L. That's what it means. And because it is a capacitor, QC points straight down, QL points straight up. So power triangle for a capacitor will be below 0. So minus 90 degrees. And for a inductor right here would be plus 90 degrees. Okay. So again, power factor is 0.5 leading, cosine of theta is 0.5, perform the reverse or the inverse operation. You obtain the power angle, and then same thing for the inductor, 0.7 lagging. And so you perform cos inverse of 0.7, you get the power angle. These are the two power triangles for the element A and element B. Now let's look at the values, or how we calculate the values for each side of this triangle. For element A, 10 kVA is given to us, meaning magnitude of S is given to us. If we have magnitude of S, we need to find theta, P, and Q. Okay, so we have 4 quantities. We need at least 2 to calculate the other 2. Right? A power triangle or an impedance triangle has the real value, the imaginary value, the hypotenuse, and the angle. Right? So 10 kVA is given for A, 5 kilowatts is given for B, but we are also given the power factor. So power factor we can use to determine the power angle theta. So once you have the hypotenuse, or one side of the triangle, and you have the angle theta, you can determine the other 2 quantities. Make sense? For element A, you are given the magnitude, meaning the hypotenuse is given to you. Magnitude of S is given. You find the power angle right here. Theta is 60 degrees. And then we can choose which equation we'd like to use. You can choose which equations you'd like to use. So again, trigonometric identities. So it depends on what you would like to use. Since we are given the magnitude of S, which is the hypotenuse, meaning VRMS, IRMS is given to us, we can simply apply the equation. P is VIRMS cosine of theta, and then Q is VRMS IRMS times sine theta. That's the first set of equations. So again, your approach, which equations you would like to use, depends on which values are given to you. Right? In this case, theta is given to us, and magnitude of S is given to us. So we can simply use the first set of equations, and we can determine P, and we can determine Q. And since element A is a capacitive load, QA should point straight down, minus. Let's take a pause. Let me know if you have any questions. Yes. So here, yeah, that is already given to us in the problem, power factor 0.5. But power factor is also cosine of theta, which we can use directly to find P. So in this case, magnitude of S was given to us, and cosine of theta was also given to us. All we had to do was multiply the 2 together. So kind of like rather straightforward, because the equation itself is given. In the second one, though, P is given to us. Cosine of theta is given, so we can do a cos inverse to find the theta for B, which is right here. Sorry, right here. Cosine of theta is 0.7. So cosine inverse of theta gives me 45.57. And if it's 45.57, I can then also find sine theta. The reason I want to do that is because, again, it's a right angle triangle. So this is PB, this is QB, this is theta, and this is magnitude of SB. So this is given to us, P is given to us 5 kilowatts, 5,000 watts. Then cosine of theta is given to us. We found theta from there. So we have 2 of the 4 quantities. We can use any trigonometric identity to determine S or magnitude of S and Q. The easiest thing is to, of course, do a tan inverse of theta, or sorry, not tan inverse, tan theta. We have theta, so tan theta and Q and P. We have theta, we have Q. Sorry, we have P, we can find Q. Right? 3 quantities in the equation, we have 2 of those, we can calculate the third. Then once we have that, we have Q and we have P, we can find magnitude of S for element B. Pythagoras theorem, the hypotenuse of a right angle triangle. And that's it. You have 3 quantities for both A, B, and A and B. You add it all up together. And this goes back to the point I made. One source in the system, but there are 2 resistors and a capacitor and an inductor in the system, meaning you have 2 average powers and you have 2 reactive powers. You add up all of them together, that gives you the total power supplied by the source, S. So SS here is all of this added up together. Q for a capacitor is always negative. So ensure, do not forget the minus sign. Otherwise, your answers would be incorrect. Okay. Once you put it all together, where's that? Source power angle. Okay. So we have PS and QS, but the question was to find or draw the power triangle for the source. So we also need the angle theta for the source. And that we can find directly from Q and S. Right? Tan theta is Q over P. You find that power angle minus 19, meaning it is pointing down. Minus 19, pointing straight down. So in this case, the capacitor is actually requiring more energy from the source than the inductor. If it's a negative, if it's a positive angle, inductor requires more energy. If it's a negative angle, the capacitor requires more energy. Right? Negative is clockwise. Positive is counterclockwise. Capacitor, negative. So capacitor is actually overcompensating. Overcompensating is requiring more energy. It's not only supplying energy to the inductor, it actually requires more energy from the source because its value is much higher. That's what's happening in the system. And that's the power triangle for the source. Okay, questions? We finished right on time. So we'll end class here today. I'd be happy to answer any questions students may have. I'll also be in my office later this afternoon. Good luck with your registration. I'll see you all on Friday. We'll review a lot of things. And then big quiz coming up on Monday. Yep, big quiz coming up on Monday. 35, 40 minutes long.